So, no surprise, we'll be talking for the same system that we're talking session. But we will be looking much more into soft impacts and in the control of the system itself. Just a brief outline. First, I'll give a little bit of objectives and motivation. That's why we're doing it, although Daniel already answered one question about that. We will talk about the system itself. I will be brief because you're already tired of it. Then I will talk about what our control methods are, how we analyze it with block exponents. We'll see about a little bit of our results and conclusions. So again, the objective that we are trying to get here is by controlling our system, trying to amplify that one behavior that we are seeing that is optimal. So we try to make it happen in a larger range of frequencies. And while we are at it, we can analyze the influence of the non-smoothness in our control method as well. So the applications of this device, as Daniel already pointed out, is not to be implemented at the grid. It's to provide energy for things outside of the grid. So, for example, in extreme environments, like when we are drilling and we have to have sensors, for example, in our tip of our drill, we need some kind of energy harvesting devices that can supply the energy for the sensors and some energy for some kind of system to send the information up. We also need to, if you have a bridge that's on the countryside and you need to have some kind of health monitoring of this bridge, you can also use these devices to implement, to provide the energy for the sensors and then have some kind of uplink. And if you like hiking, as we are in Scotland, we always do, you can use this kind of harvesters while you are walking to charge your phone or something like that while in the middle of the mountain. So that's the basic application of those devices. So again, you already saw it a lot of times, but this is our device. It's a case. We have these two membranes which provides the impact, and we have this wall that goes back and forth. You have seen so far just basically the hard impact models. However, we in this case, we are dealing with the soft impacts. So we are implementing the soft impacts. So we have compliance of the membrane. However, if you saw our experiments, we measured or fixed in having this coefficient R here. So we actually need to some form of calibration between a hard and soft impact model. So stiffness we can vary, is fine. However, the damping coefficient becomes critical when you're doing with restitution coefficients. So for a soft impact case, we can define some kind of pseudo restitution coefficient, which is basically the division between the velocities right before and right after the ball is in contact with the membrane. And if we do the calculations without any kind of excitation, we can then find a relationship between our damping coefficient and this pseudo restitution coefficient. And then we can basically set this calibration by setting our pseudo restitution coefficient as equal of the hard impact model. So we do this calibration. And I will not talk about this because Daniel already told us about, but this is the equations to calculate the energy of that we extract. At the end of the day is basically a proportional between this difference of the maximum capacitance and minimum capacitance, which is basically translated to how much this membrane is deformed. We can also measure or how much energy we're extracting for different ways. We can measure by the energy by impact. If we want, we can measure energy by period of excitation, which gives a little bit of efficiency, or we can measure just power as well. Here we'll be seeing more about energy per impact. So I won't talk about much about the dynamics of the systems because we already have a lot of talks talking about the dynamics of the systems. But what I want you to be aware of here is that you have this very efficient energy generation at this period 1-1 motion here, which is depicted here. And the idea is basically how we can expand this region, because if we see here, we have this chaotic region which produces almost no energy. And if we see this chaotic region at the beginning here, although it produces a reasonable amount of energy, it basically stagnates. So you have a trending upward motion and then you stagnate. So can we expand this one motion into these chaotic attractors? So the first thing is how we do it. Well, we can use control to do that. And basically we can do it with time delay feedback control. And if you are interested in the dynamics of the system and this difference between hard and soft impact models, you can look out this article. So how we control our system? We can use an efficient control, which takes advantage of the dynamics of the system, so we don't expend energy to generate energy. So we want to basically we want this control signal to be as lower as possible, so we don't consume the energy we are producing into this control, and actually extracting more than we are inputting on our system. And the idea of time delay feedback control is basically feeding back our system with a delayed observation. And this delay here, tau, is usually the period of the orbit that we are trying to stabilize. So this control method, because it takes advantage of the dynamics of the system, is energy efficient, also requires very minimum knowledge to be implemented, although we can need to set this gain scale. But you can see here that we only have observations and delay, so we don't need any kind of state estimator or something like that. However, because we are introducing delays into our system, we now are dealing with delay differential equations, which is a little bit more harder to analyze. But we can also analyze with Fouquet theory. So how we evaluate how good is our control? We use Fouquet exponents. So if we are analyzing an orbit that's controlled, if any kind of Fouquet exponent is positive, it is unstable. If all of them have real parts that are negative, so it's stable. And if any of the Fouquet exponents have a zero real part, then we go to the imaginary. If the imaginary is zero, it's still stable. The rest are unstable. And why use Fouquet instead of Lyapunov? Well, for delayed systems, usually our methods for to extract Lyapunov, they are very costly, and they usually give us only the real part of the Lyapunov exponent. While if you use Fouquet, we can get the real and imaginary part, so we have more information about our system as well. So if you see two cases, we test two cases, one for low stiffness, one for high stiffness. So basically here we have 0.56, 5.6 newtons per meter, and is 560 newtons per meter. And basically what we see is that we can stabilize when we have a soft membrane, but when we have a more stiff membrane, we cannot actually stabilize the system. And why is that? If we trace the Fouquet exponents for this orbit and for this gain, the control gain kV here, you see that by changing our stiffness, we actually basically reduce the initial maximum real value of Fouquet exponents, indicating that we are reducing the instability of the orbit to the point that if we lower a lot our stiffness, this is the case of 0.556, we basically destroy that attractor that we see, and it's already a stable solution of the system. So that's why, and if you see the trends in the control, what happens is that we can reduce the flow exponent, but we cannot reduce enough the flow exponents for high values of our stiffness. And only for 5.6, we have this little region here, which is our orbit is stable. Okay, so that calcium attractor doesn't work very well. Let's try the other one. So here we didn't have luck. Let's try this one. And this one is a little bit intriguing because it is basically formed by two types of orbits. You have this kind of very, I would say, even non-impacting orbit. So it's basically our ball is stationary in one point, just circling around. Or we can have this impacting orbits here, where it's basically hitting 2 times at the left, 1 times at the right, in a period of 3 excitations. Okay, let's try to aim our controller for that and see what happens. So we are targeting this blue line, and we see we actually stabilize this black. Oops. So what's happening here is that we are putting a period 3 on our control, but it's actually stabilizing a period 1. So okay, we didn't also manage to control the system like that, but why? So the reason for that, we know the reason for that. So basically, if you go to this paper, recent in preparation, published soon, what you have here is that when dealing with TDF, and imagine that you're trying to stabilize a period nj orbit, and imagine the n equals 1 here, and j equals 3. What happened in our case, because we have a period 3 and we're stabilizing period 1, what happens is that we aim for the period 3 and we can stabilize the period 1. And this happens because we don't have a shift. You can see here, this is the flow exponents for if we have j equals 1 and j equals 3. And basically, we don't have any kind of difference in this structure. So our control doesn't basically realize which one is stabilizing what. However, not all things is lost, because if our j is even, we can shift these imaginary parts of our flow exponents here, so basically the zeros, and what you have, you create a barrier. And this barrier doesn't let your leading flow exponent to actually pass through the positive side. So you cannot stabilize. For example, if you're aiming for period 2, you will never stabilize a period 1. However, if you're aiming for period 3, you can stabilize a period 1. Okay, so basically, let's try bifurcation. If nothing works, let's try bifurcation control. So again, same thing. We set parameter gains as optimal as we can, and we basically the bifurcation control. So this thing, this in black is our system without control. In red is our system with control. And at the end of the day, we actually manage to amplify the region of frequencies. However, it's 0.5 hertz. So at the end of the day, although TDF is very good for some applications, on this actual application, it's not. So basically, we need to have some kind of modification of TDF or some kind of other type of control for this kind of scenario. For example, OGY will be another control to test. Just to conclude, although TDF is a very promising controller, and actually it's almost like it's a very good candidate to be an equivalent between of what PID is for linear systems. On this particular case, it doesn't work very well. We only had a very small increase in efficiency by implementing verification control. And we didn't even mention, I didn't even mention how much my controller was actually consuming in energy. So this is also something that we need to consider here. This is a work in progress. But now all hope is lost. We can still have a lot of modifications of TDF and a lot of room, and now a knowledge of how to analyze TDF to actually propose better controllers based on time delay. Thank you very much.